Hi, this is the second example of Hess's law, also known as the law of additivity. Now, in this equation, we're going to find the delta H value for the decomposition of butane. And we're going to use three formation equations, unlike two from the previous example. Okay, so again, our target equation is the decomp of butane. So we have 1 mole of butane, 6.5 moles of oxygen. This will yield 4 moles of carbon dioxide and 5 moles of H2O gas. Okay, and here are all of our given equations. Okay, now what I suggest is you focus on the first species of your target equation. So this would be the butane, C4H10. Okay, notice that you find the C4H10 in the first equation. However, it is on the product side and we want it on the reactant side. So we're going to take that given equation and we're going to flip it. Now, when you flip an equation or you reverse it, you have to flip or reverse the sign on the enthalpy value. So our negative 2,672.5 kilojoules per mole now becomes a positive 2,672.5 kilojoules per mole. Okay, now in our target equation, our second species is 6.5 moles of oxygen gas. When we look at our given equations, hopefully you notice that the oxygen gas occurs in the second given equation and in the third given equation. When this happens, it's kind of tough to decide which equation to use. So what I would suggest is you skip the oxygen and you move to the next species. So in this case, we're going to move to the product side of our target equation, and the first species on the product side is carbon dioxide. Now, when you take a look at your given equations, you notice that carbon dioxide occurs on the product side of the third equation. Okay, but there's only 1 mole there. So we need to multiply that entire equation by 4. So we do that and we get 4 moles of carbon solid, 4 moles of oxygen gas, and now we have our 4 moles of carbon dioxide, which is what we want. Now remember, enthalpy is an extensive property, so if we multiply any given equation, we have to multiply the given enthalpy value by the same amount. So since we multiplied the equation by 4, we have to multiply our enthalpy value by 4 as well. Okay, now before you continue on, you should add these equations up and try and simplify and see where you're at. Okay, so I'll draw my line below this. Now I want to add these equations up, but before that I'm going to try and cancel out any common species. You don't have to do it right now. You can do it after you add them, but sometimes you're going to get a really long reaction if you don't try and cancel at this point. Now, what I notice here, in the first equation, I have 4 carbon solid on the product side. In the second equation, I have 4 carbon solid on the reactant side. So since the species are identical and one occurs on the product, one occurs on the reactant side, I can cancel them out or eliminate them. So I'm going to get rid of them. Okay, I check for any other common species. I don't see any. So now I'm just going to add up my equation. I have 1 mole of butane plus 4 moles of oxygen gas, and when I add up my products, I have 4 moles of carbon dioxide and 5 moles of hydrogen gas. Okay, I also have to add up those enthalpy values. So a positive 2,672.5 plus 4 times negative 393.5 will result in an enthalpy value of 1,098.5 kilojoules per mole. Okay, so now at this point, look at my target equation. Okay, I've taken care of the butane. I'm skipping over the oxygen for now. I've taken care of the carbon dioxide. Okay, the next species I'm going to focus on is the 5 moles of H2O gas. Okay, I take a look at my given equations and I notice that the H2O gas only occurs in one equation. That happens to be the second equation, and it's on the product side. Okay, but there's only 1 mole and I need 5. So I multiply that second equation by 5, which yields 5 moles of H2 gas. Okay, then I have 5 times 1/2 of oxygen gas, and that will yield the 5 moles of H2O gas. Okay, now I know a lot of you don't like fractions, but if you come back to that 5 times 1/2, that's the same as 5 over 2, which is equivalent to 2.5 or 2.5. Okay, just remember that. Now, because I multiplied that equation by 5, I have to multiply the enthalpy value by 5 as well. So now I have 5 times negative 241.8. Okay, at this point I'm ready to add these equations up, so I draw my line. And again, I'm going to look for species that are common to either the product side and the reactant side. Okay, so when I take a look at these, I notice that I have 5 moles of hydrogen gas on the product side of the first equation, and I have 5 moles of hydrogen gas on the reactant side of the second equation. Okay, species are identical and we have the same number of moles, so we can cancel those hydrogen gases out. Okay. Now I take a look, I don't see any other common species, so now I'm going to add these guys up. So I have 1 mole of butane. Now 4 plus 2.5 moles of oxygen gas gives me 6.5 moles of oxygen gas. This yields the 4 moles of carbon dioxide plus the 5 moles of H2O gas. Okay, I also have to add up my enthalpy values, so 1098.5 kilojoules per mole plus 5 times negative 241.8 kilojoules per mole will result in negative 110.5 kilojoules per mole. Okay, and that's our target equation. So with this example, even though you had a fraction in there and you probably were all freaking out, it worked out very nicely in the end.